Great. Thank you very much for making time for today's lecture. By now, you would have been introduced to the concept of volume and temperature already, and we're going to just talk more about it and help you understand it better. That is the whole concept of this video. Hopefully, you went through the Beyond labs. It started with a good lab to introduce you to volume and temperature. So you want to go through this. Make sure that you are free from all distractions. Okay, this is just like you're in class. Don't worry about it, mute yourself because we're not on Zoom, but make sure you're away from distractions so that you can focus on what you're studying today. You do yourself a disservice if you don't focus and just do whatever you want. Yeah. So please let's try and do that. And let's respond to our borrowing. So I want to know what you think from all you've been doing from Beyond Labs. What is the relationship between volume and temperature of a gas? A prompt is going to show up and you're going to put your answer there. What do you think is the relationship between volume and temperature? So let's answer that. Great. By now, expecting that you've answered this. So we're looking at volume. We've been comparing so many quantities and we're looking at volume against temperature. If I have a volume of gas at a specific temperature, what will happen if I reduce volume? Or what will happen if I reduce temperature? Would they be reducing proportionally or they'll be inversely proportional? That's what we're going to try and find out. Will this statement would it be equal to or not equal to? Meaning that if it's equal to, we're saying that when volume decreases, temperature decreases, or when temperature decreases, volume decreases. And that's what we mean directly proportional. If it's not equal to, we're saying that when volume decreases, temperature doesn't also decrease. Temperature might increase. So we want to see the relation between the volume and the temperature of a gas at a particular pressure. So that is the caveat here. It should be at a constant pressure. If you realize for all the quantities we've been looking at the relationships, there's always a constant property associated with the relationship. So for example, when we're talking about pressure and volume, there was constant something, maybe constant temperature. In this relationship, we're saying that the relationship between volume and temperature at a constant pressure. So let's keep that in mind. And um if there's any housekeeping from last week, it'll be that I want to take you through a quick description of how to draw graphs. So let's just go through it. So we've been trying to we finished Boyle's law, we finished Gay-Lussac's law, we're on Charles' law now. We want to finish that and get into Avogadro's law. Then we can have the combined ideal gas law. Great, great, great. So that's what we're going to do today. But today we're going to focus on the Charles' law. And we want to get into this. Now, I'm just doing a short housekeeping. Now, from what you did in Beyond Labs, I realized that a number of you were struggling on how to generate a graph. I'm thinking that inside Beyond Labs, there was a way to generate a graph inside Beyond Labs, but some of you are struggling with that. If you can, there's a popular, you have two ways to draw a graph. Sorry about that. If you're going to draw a graph, first of all, you need data. Let's say I have X values and Y values. I'm going to just take you through this real quick. You're supposed to have done this in math or physics, and I teach chemistry, but I'm just going to help you out. So let's say I have X values. Maybe the X stands for, um, let's say volume, and Y stands for temperature, T. Let's say we have 2 here and we have 8 here, then we have 5 here, then we have 14 here, then we have 10 here, then we have 25. Okay, I'm just giving you an example. Let's say these are the values. You want to plot these on a graph. If you want to plot that on a graph, there are two ways to go about it. You can either use a physical, like we have the traditional way of going about this. We have the traditional way of going about this. The traditional way is to draw it with a graph sheet, or you can use Excel. So Excel is So Excel is doing the work of a traditional graph sheet. So it's the same thing. So both ways, first you need to have a data. So let's say if you're using Excel or if you're using a traditional graph sheet, you have your data for your X values and Y values. The next thing you want to do is to insert. If you're using Excel, you're going to insert a graph. You have to choose a graph that has X coordinates, X values and Y values. Okay, that's if you're using Excel. If you're not using Excel, you just need to have your graph sheet. Graph sheet is normally a plain sheet that has a lot of grids. It has a lot of grids. So normally you're going to draw. Most of the time, you don't know if your graphs are going to have negative values or positive values. So there's a traditional way to go about it. You start by drawing your axis in the middle of your graph sheet. That's when, if you don't know whether you're going to have negative or positive, you draw your axis in the middle of the graph sheet. So you have this as your Y. Your Y axis is normally the vertical. Your X axis is normally the horizontal. Now this is in case you have a negative values in your data. Then you're going to have negative values here. You get it? Great, great. In your Beyond Labs, there were negative values, or there's likely to be negative values. So and that's why I'm doing this to show you how to go about it. And you have this for negative Y values, so that you can plot them on the graph. If you are not going to have any negative values, you can just straight away plot your axis, draw your axis this way. So it takes up the whole space of the graph sheet. This if you're doing a traditional graph sheet. Okay. So let's start. Let's say I plot my values. On Y, I have 8. So I look for 8. Let's say this is 8. On X, I have 2. So let's say this is 2. I plot my first value here. This is my first value. The next value, I have 14 on Y. So let's say 14 on Y. This is just an example. So it's not going to be exact. Forgive me for that. And let's say I have X to be 5. So let's say my next value is somewhere here. Then now my last value is, let's say I have 10 on X. So let's say 10 here. And I have Y to be 25. So let's say this is 25. Once again, this is not drawn to scale. So for every graph sheet, you need to have a scale. So if you look at this graph, the next thing to do is to join all your points together. So when I join all my points together, I have a graph like this. Okay, it's a straight line. And so this is to tell you that your relationship is a linear relationship. That's what we call a linear graph. What that means is that when one quantity or one value or one coordinate is increasing, the other is also increasing. So if my X values are increasing, my Y values are also increasing. That is to establish the relationship between the two quantities you're representing on the graph. In this case, you're representing volume and temperature as our example. Now, this line is your graph. Now, when you extend this graph, you see this graph here, we call it, you can extend the graph or extrapolate it. So I'm going to try and extend the graph like this. You see that? I just extended this graph further. Now, when you extend it further, you see it hits your x-axis here. Okay, where your graph intersects your x-axis, we call that the x-intercept. We call that the x-intercept. We call that the x-intercept. In one of your on your graph question, there was a question that asked you for the temperature, and it said that it is when your graph intersects the your x-axis. And some of you didn't know the answer. I saw that some of you were making mistakes. That's why I'm doing this. That question was asking you to. So that's basically why I'm going through this to remind you. So that question was asking you to give them the value of I think it was the temperature, and it added information to tell you that it is where your graph intersects the x-axis. So in that case, this will be our x-intercept. and that's the value they wanted. Now, if you are using Excel, all you have to do is to tell Excel to generate your equation of a line. We call that equation of the line. Now, for every line that you draw on a graph, in a linear graph, we can represent it by this equation: y equals mx plus c, where c is your x-intercept. So in this question, what we were looking for is the value of your x-intercept. This stands for your gradient. As I told you, you're supposed to have learned this in math or physics. I'm just teaching you chemistry. Gradient. If you want more about this, we can do this in another lesson. I'm just helping you. So if you're using Excel, you tell Excel to show you your x-intercept, or you should just give you the equation of the line. When Excel gives you the equation of the line, whatever value you have for the equation of the line here, that will be your x-intercept. In the question we had in Beyond Labs, it was supposed to be minus 273, I think, because the graph was intercepting at, that was where the graph was intercepting the x-axis. So it can be a possible negative depending on wherever the graph intercepting the x-axis. In this case, you can see clearly that our graph was intercepting x-axis on the negative side. So our x-intercept is supposed to be a negative value. If the graph was somewhere, let's say the graph was this way, it would have cut it here. Then we know for sure that our intercept is going to be a positive. But in this case, this is our intercept. So that value is what they were looking for. Okay, I hope that made sense. Now, I'm going to go straight into Excel and just show you an example if you were using Excel. Okay, I'm just trying to help you guys. So let's do that real quick. I'm going to try and go into Excel so that you can see how you do it if you're doing Excel. Okay, this is one of your friends who used Excel. So this is what we're trying to do. So I'm just going to I'm going to take your friend's values and take you through how to drive with Excel, everybody. I hope that makes sense. So copy. So let's say I'm going to generate a new sheet. This is you open Excel. For example, you open Excel. Now the data from the lab. So the lab gave you values for temperature and values for the volume, right? Yeah. So I don't know if you were supposed to in the lab, if they didn't tell you to convert, that's fine. But when we're doing the calculations, we need to convert the value into Kelvin scale. Okay. So let's say I have liters, I have temperature here. So the two things I can do, I can convert my temperature into Kelvin scale. Let's see how we go about that. So I'm going to put T here, and I'm going to put, oops, I'm going to put K. That means that Kelvin scale. It means that I want my values in Kelvin scale. And I'm going to put a formula here to tell Excel to add 273. Remember, if you want to convert something from degrees Celsius to Kelvin, we said that you do what? You add plus 273. I want to be exact, so let's say I want to be exact. So um if you want to be exact, it's your degrees Celsius plus 273 point something something something. So we want to be exact. So let's do that. So let's do that. So it's going to be your Celsius value plus 273.15. Okay, great. So this is what we're going to get. And I'm going to tell Excel to do the same for all of these. So Excel just took my values in Celsius, converted them to Kelvin. I think if I didn't convert it, my graph would be okay though. But whatever value I get is going to be in Celsius and I need to convert it to Kelvin. So keep that in mind. Okay, that's just to help you guys. Okay, so now let's try and plot. So there are a lot of ways to do it. You can go to insert, then you tell Excel to insert. So you can do this, highlight the values you want to be represented in the graph. I'm highlighting Kelvin and the liters because I converted the Celsius to Kelvin. You could have still used Celsius and the liters, and I think your graph is still going to be correct, except that the values you get in Celsius, you need to convert them to Kelvin. Okay, so I just highlighted this. I want to tell Excel that I need a graph. Okay, so it give me options of the type of graph. You see, now I want a graph that has X and Y, and this is a good example. You see this? So you choose, they give you a lot of options. Excel has an option where they just plot the point without drawing the line for you. This is going to plot the point and draw the line. This is just going to give you a smooth line without seeing the point. So we want to see the point. Scatter with smooth lines and markers. So we're going to go with this. So I'm just giving an option to see all the different options. So let's do this. Tell Excel to do this for us. And straight up, Excel just drew the line for us. So we know that this is a linear graph. You see that? But now we can do a number of things to this. We want to see the titles. So I can just do titles and I want to write the name of the title for this. It's supposed to be, so the question we need to ask ourselves is, we need to try and figure out which is the X, which is the Y. So from the graph, we can tell that, so let's try and figure that out together. My first X value was this, 3.73 raised to the power 10 raised to the power 2. Okay, so this is 3.73. So this point, so you can just place your mouse here and it's going to tell you which point that is. It's saying that there's the point for 3.73 as your X and 1.5 as your Y. So this is our first point. So means that this is our X axis and that's our Y axis. Normally the X axis is the first point they plot. Okay. So it plotted 3.73 first. So it plotted these values as the X, these values as the Y. Great. So this are X value. So I know that this axis is going to be the temperature. So I just do this. I want to name the axis. So this is just naming. I'm going to say, good. So I'm going to say temperature. Then you can put in bracket here. I'm just showing how to use Excel to do that. Kelvin. Then you can go here and do this volume. Volume, right? And our volume was in liters, so I just bring L here, liters. That is to say that whatever value I get, if it's on the y-axis, I know it's in liters. If it's on the x-axis, I know it's going to be Kelvin because I already converted mine to Kelvin. If you didn't convert yours to Kelvin, then yours is going to be in a different whatever value. Okay. Now the next thing I want to do is now I want to remember we said that we want the intercept, right? So these are just the data to show us the data. I don't know if you want the data. It's going to make the graph look ugly, so you don't have to attach the data. Now we can ask for the trend line. Now the trend line is what helps you to know the equation. Okay. So I just asked for the trend line. Yeah, so I want to see the equation. So look, so you see when I clicked on the trend line, it opened this. They're telling you format the trend line. Now I know my equation is a linear equation, so that is selected linear. Then I go to automatic. Now they're asking for um how I so here they're going to try and extrapolate the line for you. So they're going to stretch this line forward or backwards to get the intercept. That's just for another day. Right now, I just want them to set the intercept and I want them to display the equation on the chart. Right? So that's what we're gonna do. So let's look at this. So that's the so that shows us the equation of the line right there. Okay, so this is the line of the graph. Now your intercept is just supposed to, it means that when you extend this line, wherever it cuts your x-axis, that is going to be your intercept. Okay, and from the graph and the data you have from your Beyond Labs, when you extend the line towards this, you're supposed to get 273, I think. Okay, so based on whatever graph you generated, your intercept is going to be something like that. And I think in Beyond Labs, you're supposed to have been able to generate your graph. I was just showing you how you could do it if you were using Excel. Okay, so I hope this helps. And if you have any questions about this, you can just let me know too. Okay, great, great, great. So this was for one of your friends though, and I used her data to give you the example here. As I said, I don't know if that was the right data or the wrong data. I just used that as an example for all of us here. Great. If you have any questions, let me know. If you have any questions, let me know. Okay. Great. So there's a way to go about this. I wanted to try and do this. Great. So I could use a line here like this. So this is the so I could use a line. So let's see. I want to use a line to generate the intercept. So I could insert a line. And what I'm just going to use a straight line. Oops, sorry. I'm going to try and get a straight line to help me gauge the intercept. Okay, so I'm just going to follow the same plot. I don't know if you can see what I'm doing. I'm just trying to get the where the intercept was. Okay, great. Now, as you can see, I want you to follow this. You see that it intercepted at exactly 0. Okay, now if it intercepted at exactly 0, remember this is on the Kelvin scale. Okay, so means that the x-intercept is going to be, so my x-intercept is going to be 0. That's what I wanted to show you guys. My x-intercept is going to be 0. It's going to be 0. Now that is 0 Kelvin. Now if you remember, to get the value of Kelvin, what did we do? We added 273 to the Celsius. So now I want to get it in degrees Celsius. What do? I take 0 and I subtract 273 from it, and that should give me the value in Celsius. Okay, I don't know if that makes sense. So I take this value here. So if you wrote 0 Kelvin in your answer in the Beyond Labs, it should be correct. Or you write minus 273 degrees Celsius and you get it correct. Okay, so that's what I was going to show you. If I use, let's say I didn't use, I'm going to try and show you something right now. I'm going to use the Celsius values, and you see that I'm going to get 273 or close to 273. It's supposed to be the same thing. So I'm converting my 0 Kelvin to degrees Celsius. Minus 273.1. Right, that's what we did. Great, and you see my answer now. So this is in Celsius. And that was the answer that we're looking for in Beyond Lab. So this is your final answer. I hope that helps. Now I'm going to try and tell Excel to do something different for me right now. I'm going to tell Excel to change my graph. Okay. Like, not really change my graph, but I'm going to try and see. Good. So you see, Excel used these values for my graph. I'm going to tell Excel to move. Oops. I'm going to tell Excel to change my x-axis values. Oh, okay. It wouldn't. It wants to keep both of them. I want to just move. Okay. Okay. He's not going to do that. Okay. Then I'm going to find another way. So you can go this way and do select data. Good. Now you come to your sheet and go to edit. So these are my x values. Okay. So it's you see, it's showing me the x values he used. I want to tell him to now use this x values. That's all I'm doing here. So I want to tell Excel to use these values now. Good. And now these are my y values. They're good, and I can do OK, and that should be OK. Great. Now as you can see, now Excel just do a new graph for me. This is the new graph using the values we had for Celsius. Now the only problem with that is because we're using the Celsius scale, you can see that my intercept, I'm going to show you guys something right now. If I try to follow this line and get a straight line for my intercept, let's try and adjust it. Look, now you can see that my intercept is going to be outside of this graph. You see that? So what that means is that it's exactly what I'm saying. This graph is only a graph showing x and y. The problem is that now you need to have the negative values. It's showing all your x and y as positives. Remember, our answer we had was minus 273. So we need to allow the graph to include negatives. Okay, so how am I going to go about that? There are so many ways to go about that. I'm going to try and follow one way. So I'm just going to extend this line. So if I had negative values, then I'll be able to tell exactly where this line cuts the x-axis. And I need to change this because I just changed it from Kelvin to Celsius. So now let's put Celsius. I don't want to be confused. So now our temperature is no longer in it's no longer in Kelvin, it's in Celsius. So let's do that. Okay, and just so you know, all of this is just to give you an idea of what the graph was looking for. Now, the second part in Celsius, you don't have to watch it if you don't want to, or you don't have to pay attention. I was just showing you how another way to go about it. Now we need to make sure our intercept is, oops, sorry. I want our intercept to be straight on the line. Oops. Great. Good. Our intercept is straight on the line. So now I'm going to try. So what I'm going to do here is I'm going to try and include negative data for x and y, and that will extend our graph. As I said, you don't have to really, if you're not getting it at this point, don't worry about it. I'm just trying to give you um so let's see, I put let's say I put a negative 273. Okay, let me do 278 rather. I'm gonna change this and make it a text. So please, once again, this is just general helping you to follow what is going on. Great, great, great. I wanted it to look like these here. Then I can have, I want to get, now I need to figure out a corresponding value. So let's see, yeah, let me try and do that here. So this is my, let's say 273 is somewhere here. What will be the corresponding? The k is going to be 0. Yeah, that makes sense. No, the y is still going to be 0, and my x is just good. So let me put 0 here. Good. Oh, no, sorry. Put 0 here. Put 0 here. Good. All I'm doing is I'm trying to add a negative to it. Okay, so let's do this together. Now I'm going to go back to the graph, and I'm going to try and select this new data. Select data, edit. I'm going to tell my x-axis to now include, um, I want to tell my x-axis to include this guy too now. Okay, so now I'm going to tell include this guy. Okay, it's not picking the value, so clear all of them. Good. Now these are our new data. Good. So I just did that right now. Okay, good. Now all of the plenty values here. Good. Now I'm going to take away all the extra lines that are bringing confusions. Take the grid lines away. Turn the grid line. Good. Good. This is what I want. And everybody look at this carefully. All I did is what I extended my axis to have negative values. Okay. So now we can plot it again. This is what I'm gonna do. Good, good. This is what I wanted. So let's all pay attention now. I just extended my values. Good. Okay. I extended my values so that it can cut this graph. So this is how it will look like if we included negative values, okay? So that I can have a negative axis. Then now I can find my answer for Celsius. So this graph, if the values we have here is right, then my graph is supposed to be touching. My graph is cutting. So as you can see, this graph is going to cut the x-axis at this point, okay? So we are going to call that particular point, we're going to call this particular point you see here as the x-intercept. So this value is supposed to be equal to 273 if everything we're doing is right. Because remember, I did the first one in Kelvin scale and I had my answer to be 0K, okay, which is the same as 273 degrees Celsius. Now, if you did your values in Celsius scale, your graph is supposed to cut the x-axis somewhere here, and that should give you your answer, okay? So that's all I was trying to do. I know this took a lot of time, but this is basically to give you an idea of how to generate a graph. For all those who are struggling with it, this is how you were going to have to generate a graph. So our answer was going to be either 0 Kelvin or minus 273.15 degrees Celsius. I hope this helps anybody who couldn't understand what was going on with the graphs. I think in Beyond Labs, there was an inbuilt way of generating the lab. Let me know by sending me a comment on the video or whatever you need me to do. If you want me to go through this same thing in Beyond Labs and use whatever Beyond Labs wanted you to do, we can do that too. Okay, great. And let's get back to the class for today. Good. So that was just to help you with understanding a graph. So remember, we've learned a number of things, how to draw a graph. We've learned the x-intercept. which you're going to use as you go further in chemistry and physics and math. Okay. So today we want to look at the Charles law. That's the main thing we're going to do in today. And we want to look at the relation between volume and temperature. That's basically what we're going to do today. So let's look at this. I don't know if this is a video or animation, but we're going to find out soon. So I think this video is supposed to, let me see if this changes anything. Okay, good. Now I was able to get this. I wanted to get this. Let's see what this link takes us to. Good, it takes us to a video. Now I want to pause this. I don't know if you can hear the sound. So let me just make sure you can hear the sound. That's what I'm going to do. I want to make sure you guys can hear the sound. So let's do this together. Um, Hopefully you can hear the sound. I guess that's the only option I have right now. So let's do this together. If you cannot hear the sound, I'm going to be giving you a commentary. So we have a balloon and a gas. So they filled nitrogen, and nitrogen, it doesn't give out heat. It takes all the heat in. So nitrogen is very cold. So as you can see, what is happening to the balloon? Great. So that's about it. We can go back to our lesson. So that gives us a good phenomenon here. Think about it. Remember, we've been talking about this a lot. We're going to just go further. So for those who didn't know that gases, so we know gases, they are their molecules are widely spaced because they are expanding. When I apply heat to it, it's going to expand faster. And let's say this is heat, expand faster, take more space. So eventually, this is going to have to become bigger because it's going to keep expanding, and it keeps doing that. Now the reverse is that if I have a gas filling this, the moment I make it cold, let's say cold. When I say cold, what that means is that we're taking heat away from it. It's going to start contracting. The gases are going to start going closer. So you see that this space, the same gas, just that the gas is now contracting. The molecules cannot, they are not agitated to keep on moving around, like they are kinetically not engaged. So with time, the more you take heat out of the system, the gases begin to contract and they become closer together, and they eventually will change from a gas into a liquid. And when they change from a gas to a liquid, they take less space as compared to what they were when they were in a gas. And that's what we saw in the video. Okay, so that brings us to our big discussion for today: the effect between volume and temperature of gases. Okay, so we're saying that if we fill, we want to read this together. If we fill a balloon with air and seal it, the balloon contains a specific amount of air at atmospheric pressure. Let's say the pressure was 1 atm. If we put the balloon in a refrigerator, that's what they just did in the video. They just found a cold medium. Nitrogen gas, the new nitrogen gas will be cold. So they use nitrogen gas. Most of your fridge has nitrogen gas in there. It helps with the freezer when it's cold. So the gas inside gets cold and the balloon shrinks. I don't know about the fridge thing I said, but basically nitrogen gas, it's going to absorb heat instead of give out heat. So if you want a cold system, just use nitrogen gas. And the balloon shrinks. Okay, so that's what we saw. And I just explained the balloon shrinks, even though the amount of the gas has not reduced. The only thing that has reduced is that we have changed something. What did we change? Once we put it in a refrigerator or in a cold environment like they did in the video, we are dropping the temperature. So if I drop the temperature in the system, it's going to affect not the amount of the gas, but it's going to affect the properties of the gas, making the gas not able to expand. It's going to rather contract. And with time, that air or that gas will change from being a gas to a liquid. And that video was perfect in explaining that. Okay. So this graph you see here, we have methane. So methane is a gas. If you don't know methane, this is methane. Methane is CH3. So we have a gas compound, methane. Now they used methane and they tried to track temperature changes with respect to volume. So they had methane at -3 degrees Celsius. If you want to convert this to Celsius to Kelvin scale, just add plus 273. And that's what they did here, and they had this. So when they had methane at this temperature, this was the volume. Okay, let's see what happens. Now they drop the temperature further. So they drop the temperature further. And now our volume also decreases. They drop it way further. So you can see that it looks like the factor of the reduction is also the same as the factor of the reduction in the volume. Okay. What is that telling us? That is telling us something about the relationship between temperature and volume of gases. They drop it way further more here, and something happens in the volume. It drops even further here. Okay, so they try to represent this data on the graph, which by now you've realized that we're going to be doing that a lot. So when they represented this data on the graph, this is what they got. They realized that on a graph, they put the values. So it's the same thing they did there. Just that what they did is that they put their graph on a Kelvin scale. Now think about it. Why do you think they put the graph on a Kelvin scale? Let's think about it. What do you think? I think they put the Kelvin scale to avoid negatives. Remember, they told us that the Kelvin scale represents absolute values. Absolute values means that there's no negative. So that's the whole point of putting the Kelvin scale. And if you remember the example I showed you, I converted my degree Celsius to Kelvin and I had no negatives to deal with. Remember? Great. So that's what they did. They converted their Celsius to Kelvin so that they don't have to deal with the negatives. When they are done, when you have your value in Kelvin, you can just convert it back to Kelvin to Celsius if you want to. So they represented these values here, 270. So what is 270? 270 was somewhere here. Let's say 270. Let's say this is 250. So this is 270. So they had a graph with 270. Oops. Yeah. So that's 270 there. And what was the temperature? Sorry, what was the volume? The volume was 22. So maybe 22 was somewhere there. And they had that point there. The next one was 250 Kelvin. So let's say 250 is somewhere here. Then now they had 21. So let's say 21 is somewhere there. Sorry. I'm just trying to, it's not drawn to scale. So that is how they got their line here. I want to explain something here. Now, what was happening is that with time, as the temperature drops, you can see the temp. No, let me do it this way. As the temperature is dropping, because as you go this way, it's 300, now it's 200, now it's 100. So the temperature is dropping. Okay. As the temperature of methane is dropping, something happens to methane. At this point, methane changes from now. If you don't know, methane is a gas. Okay. But as the temperature of the gas decreases, so we are dropping in temperature as we go this way. As we drop in temperature, at this point, at the temperature of 111 Kelvin, methane crosses over from being a gas to become a liquid, just like we saw in the video we watched, and that makes sense. Okay, so at this temperature of 111, methane, which is a gas, has now converted to liquid. So we can have liquefied gas, we can have liquefied air. It's just all a matter of what temperature changes and how the temperature affects the volume. And so now going in the short dashes, all of this side, we have methane existing as a liquid instead of a gas. Great. I hope that makes sense. I hope this is helpful. And just so you know, the amount of the gas has not changed. The only effect is the effect of temperature change on a gas. And that's what a very great scientist called Charles. So this law was named after him. He came up with this law saying that the volume of a given amount of gas, so the volume of a given amount of gas is directly proportional. Now back to this word again, directly proportional to its temperature. And he wanted us to keep the temperature on the Kelvin scale. Why? Because on the Kelvin scale, we don't have to deal with negatives. That's the whole reason why. Because once you use Celsius scale, everything you have to add 273 to get it in Kelvin. Okay, great. So we know his proposition or his law was that volume is directly proportional to temperature. Okay, now this is just a proportionality statement. We're going to have to now convert this proportionality statement into a mathematical equation. So how do we do that? We're saying that anytime you have a proportionality statement, if you want to convert it into an equation, we need to introduce a constant. So we're saying that volume is directly proportional to temperature. Then we can say that volume will be equal to, then we introduce an equality constant, okay? So our constant here is the K, so that we can bring an equal to sign. So we're now saying volume is equal to K times T. Okay, now if we want the constant to stand on its own, then we're going to have V equals KT. Now divide both sides by T, divide both sides by T, so that this T can cancel this T. Then now we're going to have K now is equal to what? V over T. Great. Now, if this is true, if we were saying that for every volume of a gas at a certain specific pressure and a temperature at a certain specific pressure, if we divide the volume by that temperature, we're going to have a constant. Now, if this is true, then we can say that, okay, then if I have a volume, another specific volume of a gas, let's say V2, let's say this is V1 at a temperature T1. Let's say if I change the volume T2, it's going to have an effect on the temperature. So we have a new temperature T2. That will also be equal to the same constant. Or we're saying it's a constant, right? Now, if 1 is true and 2 is true, then now we can write that K is equal to K, which means that V1 over T1 can be equal to V2 over T2. Great. Remember, on Kelvin scale means that our temperature should be in Kelvin to satisfy this. Okay, on Kelvin scale. Great. So now this is our final equation we can derive from Charles' law. Remember, we've been deriving equations from all the laws. The ideal gas general equation is going to be a combination of all the laws. Okay, great. So I want you to pay attention to this. All this while I'm expecting that you're writing notes. If you're not doing that, you can go back, write down certain stuff you're learning from this, put it down in your notes. Okay, so you can write this now, and that's why it's a video. You can at any point in time you can at any point in time you can pause the video or watch the video again and again and again. Okay. Great, 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 great. So we can move on then. So we have a question here. I want you to write this question down. We're going to try and solve this question. I am going to do this with you. I'm going to take you through this, but then after this, I want you to also now do it on your own. I'm going to give you one to try on your own. So that's the exciting part of this. I know you love to try it on your own. I know we all like to try it on our own. So let's read this question together. I want you to take your time and read this question. So hopefully by now you're done reading this question. Great. If you're done reading this question, then we want to go into it. We're going to do it together. So let's go. We're saying a sample of carbon dioxide. So our gas is what? Carbon dioxide. Always pay attention to that. Our gas is carbon dioxide. It occupies 0.3 liters. So what is 0.3 liters? I'm assuming you know that liter stands for volume. So 0.3 liters is volume. That's the first part of it. And they're saying that the gas is occupies this volume at this temperature. So I have a temperature value which is 10 degrees Celsius. Okay. And now at this pressure, the pressure is 750 torr. And the question says, what volume would the gas have at 30 degrees Celsius? So now they're giving you another temperature, the second temperature. So let's say if this is the first temperature now, there's been a change to the temperature. There's a second temperature. The second temperature is now 30 degrees Celsius. Now, from what we learned about the Charles law, we know that when the temperature decreases, the volume is also going to decrease. Or when the temperature increases, the volume is going to increase. So we're expecting an increase in volume. Keep that in mind. That should guide you. So if your answer is not an increase in this volume, it means that there's something wrong somewhere. And they're telling you that it's at the same pressure, so mean constant pressure. That satisfies Charles's law. So straight away, we're going to try and solve it. But before we go into it, remember we said we need to have a temperature in Kelvin scale to help us apply it to Charles' law. So let's change this temperature to Kelvin. It's going to be 10 plus 273.15, and that's going to give you 283.15 Kelvin. Do the same thing to this one here. We're going to have 30 plus 273.15. Right? Great. Then now we can, what will be our answer? It's going to be 303.15 Kelvin. Now the rest is the formula. Remember, our formula says that V1 over T1 should be equal to V2 over T2. At least, is that what our formula said? Yes, that's what our formula said. So we're on track. Now, what we are looking for is what? V2. That's what we don't know. We don't know V2 because they said what volume. So let's say we don't know oh, sorry. I was trying to put a question mark here. So if I want to make V2 the subject, what I can do is that I can just I can multiply both sides by T2. Why am I going to multiply both sides? Because T2 is dividing here. So if I multiply both sides by T2, then I can have V2 to stand alone. So let's do that. We're going to have V1 over T1, but I multiply this side by T2 equal to V2 over T2. And I multiply this side by T2. That's what we're doing. So that T2 cancels T2. T2 go here, cancels out by 1, right? So we're going to have V2 to stand alone. Okay, let's go to next. So now we're going to have V2 to be equal to, go back and watch the formula. V1 T1, V1 over T1 multiplied by 2, T2, and that's our integrate formula. Now all we have to do is just substitute the values from this point. So what is our V1? V1 is 0.3 liters divided by, what is our T1? Oh, sorry. What's our T1? Our T1 is 283. Remember, we're using the Kelvin scale. 283.15. So 283.15 K multiplied by, what is our T2? 303.15. So 303.15. We're using the 0.15 because we want it to be exact. Some textbook will just say add 273, and that converts it from Celsius to Kelvin. Some textbooks, but the exact value is 273.15. And that's what we're using. So first of all, K can cancel K. So of course our answer is going to be in liters for sure. Now the rest is a calculator. So what's my calculator? I'm going to grab my calculator here. And let's do this. I'm going to do this real quick. So I have 0.3 divided by 283 0.3 divided by 283.15 multiply by 303.15 again, and that gave me great an increase in volume. I had 0.32 2 1 It's a lot, 119 liters. I can just approximate it. That sign, that wavy sign simply means approximated. I'm gonna have V2 to be equal to 0.32 liters. Great. What does that tell us? That tells us that our volume, when the gas temperature is increased. So that tells us that when I increase the temperature of the gas to 30 degrees Celsius, I'm going to do something to my gas. My gas is going to expand rapidly, and now it's going to occupy more volume. So it was occupying 0.3 liters. Now it's occupying 0.32 liters. Now, if you don't know how much an increase has happened, you can convert your volume into another volume unit that you are familiar with, and that help you to know the increase. But that is our final answer, and I hope you had a good time following this video. You're going to try this on your own. A screen is going to pop up asking you to try this, and I want you to try this on your own. Try this, follow the steps, write it in your notebook, because you're going to have to put this into Canvas. I just created an assignment where you're going to put this answer into Canvas. So either way you do it now, so that you already have it, then you can put it into Canvas also for extra grade, to get your grade for that particular assignment. But it's the same question. And I hope you have time. Take your time, watch this video. If you didn't get anything, go back, watch it again until you get it. Continue going back to watch it. Okay? Great, great, great. I hope you have a great, great time.